Hey, how you guys doing this wonderful afternoon? Well, it's sort of wonderful. This is Mr. Myasis here. And the reason I say sort of wonderful is I am suffering from a bit of a cold. So if you hear me cough a little bit here, or I sound a bit different, that, my friends, is the reason. So in this video, anyway, besides my cold here, in this video I want to talk about solving some problems involving exponential growth and decay. So we're looking at application problems, folks. We use exponential functions in investing money, buying a house, population change, loss of value, carbon dating, and also, like looking at the spread of viruses, things like that. And carbon dating is, looking at how old things are that are in our grounds. So let's take a look at some application problems, okay? We're going to do this basic. When you get into pre-calculus and calculus, they do things even more intense, I should say, and in-depth. So let's take a look at some examples. So here's just a reminder what exponential growth is. Exponential growth goes up like this, and it grows exponentially. And decay comes down and gets closer and closer to zero. All right? So this is our growth and decay formula using an E. Y here, this is your final amount. That's the population or whatever you're left with. A is what you start with, your initial value or beginning amount. K is a constant of growth or decay, and normally we're looking for that. That's going to be different numbers for different things. And T is time, and it depends on what time value you're using. So this is our first example. The half-life of sodium 22 is 2.6 years. 2.6 years, that must be T. So T is 2.6. What is the value of K? K is what we're looking for, right? For this element, we're going to round to 4 decimal places. So here's what we're going to do. We're going to use our formula, y equals a e to the kt, and we're going to plug in what we know. So first thing I need to tell you is what is half-life? Half-life is how long it takes for the substance to have half of what it started with. This substance is decaying because it has a half-life. So what that means is my end value is going to be half of my initial value. This is my initial value A. My y, my end value, is going to be half of whatever that was, A over 2. So for half-life problems, we can write it like this. 1/2 is equal to e to the kt. And you're probably saying, Mr. Myasis, what happened to the A? Well, this is what happened, guys. I substituted A over 2 for y, and I divided both sides by A. And you see the a's cancel out, and I leave with 1/2, and these are gone too. Okay, so that's usually what happens when we're dealing with half-life. We can just skip that step and go straight to this. All right, so what are we going to do here? We got to make some substitutions. 1/2 equals e to the k times t, which was 2.6. And we're going to solve for k. Solving for k here, we want to take the natural log. So the natural log of 1/2 is equal to 2.6k. Guys, this is just solving the equation, solving the exponential equation. We're using an ln because we got an e here. Then I divide by 2.6. So k is ln of 1/2 over 2.6. I use my calculator to figure that out, and that comes out to be negative 0.2666. Ooh, scary. That's my k value, guys. Let's take a look at the next one. Particular type of bacteria has a k value of oh, look, we're given the k value now. If there are 750 bacteria at the beginning, okay, that would be A. How many bacteria will there be after 9 hours? That's our T. So let's go and plug in what we know. We don't know why. We do why? I don't know why. Because we will find out. 750 is A. E to the K. K was 0.2357. Since K is positive, just a side note, this is going to be a growth formula. When K is negative, like the last one, we had a decay formula. So we're going to plug this guy in our calculator, and we are going to get 6,256.48 bacteria. That's a lot of bacteria, guys. Bacteria multiplies like crazy. Make sure you go to the doctor if you have bacteria. All right, a biologist studying animal population has this down. This is a little bit different, doesn't have an E, but this is our formula here. We're T is in years. How long will it take for the population of 800 to grow to 10,000. All right, so this is our initial, which in this case is B, right? It's the number multiplied there. And this is our ending, which is 10,000, which in this case is A. So we're going to have 10,000 equals 800 times 3.2 to the 0.843t. And we're going to solve this guy. So we're going to divide by 800 first. Divide by 800. Then we're going to take the log of both sides. Log of 10,000 over 800 equals log of 3.2 raised to the 0.843 times t. Bring this down to the front. Log of 10,000 over 800 equals 0.843 t times the log of 3.2. And we're going to divide all this stuff that's not a t to this side. So we're going to have t equals log of 10,000 over 800. Okay, that's all inside the log. Divided by 0.843 times the log of 3.2. And we're going to figure out what that is in our calculator. And that is going to be 2.5759. Oh, it says round to the nearest tenth. All right, so 5.6. 2.6. All right, let's look at another one. So these are other type of growth and decay formulas, and we use these for banking a lot of time. So you'll see these as banking formulas. The population of a city, well, I guess I'm using population here, has increased a rate of 3%, so that's R, and we're going to make that 0.03. We got to put it as a percentage. If the population continues to grow at this rate, how many years will the population have doubled? Double of a million is 2 million. So let's go and write that down. Y equals 2 million. A is equal to 1 million. 1 plus 0.03 raised to the t. I'm going to divide by 1 million. By $1 million. That's my worst Dr. Evil impression. 2 million divided by 1 million is just 2, right? I think I did that math right. Alright. Okay, let's change this to log both sides. So log 2 equals log 1.03 to the t. So log 2 equals t log 1.03. Divide log by both sides there. So log 2 over log 1.03, and that will be in my calculator. It will give me 23.4. It says round in there is tenth, so we'll leave it at 23.4 years. Alright, guys, I'm going to leave it at that. We got one more here. If you want to take a look, I'll do it, but otherwise we'll sign off. This is Zeus Industries, bought a computer for $2,500. It is expected to depreciate at a rate of 0.20. Depreciate means lose value. What will the value of the computer be in 2 years? Okay, so I don't know the value of the computer in 2 years, but I do know that it cost me $2,500. It's going to depreciate at 0.20, which is my percentage. And I'm going to do that for 2 years. So I'm going to have 2,500 times 1, oh, not 1, times by 1 minus 0.2 is 0.8, right? Raised to the 2 power. I'm going to put that in my calculator, and I'm going to get $1,600. Dollar bills. So my computer will depreciate in value, and it will only be worth $1,600 in 2 years. That sounds about right. Computers don't last very long. All right, guys. That's it for me. See you later. Bye-bye.